Alright, welcome to our first video for Chapter 2, Lesson 2.1 over Inductive Reasoning and Conjecture. In this lesson, we are going to introduce some of the concepts used in Chapter 2 and look at patterns, things like that. And this chapter, Chapter 2, will be a little bit more like an English class on some days because we will be making statements. You'll be kind of lost as to where the numbers went on certain cases, but we are looking at logic and reason, which is a mathematical concept we need to use, and in fact we're setting the foundation for a lot of these statements and reasons that we're going to be using throughout the rest of the year. So let's get started. In the past, you have used data to find patterns and make predictions. Now you're going to be making conjectures based on inductive reasoning. We're going to identify both those terms here in just a minute. But you also have another vocab word later on in the lesson called counterexamples. We're going to be finding counterexamples. So let's take a look at some of this terminology. All right, we have this term inductive reasoning. That's your first highlighted word in this lesson if you're read through your book already. Hopefully you have these definitions written down in your vocab book. If not, you'll want to do that in the notes and the vocab book. Inductive reasoning is reasoning, which is another way of saying coming to a reason for something happening, coming to a conclusion about how something works. Reasoning that uses a number of specific examples to arrive at a conclusion. We call that inductive reasoning because you're basing it on specific examples, like patterns. Then the word conjecture is that conclusive statement, that conclusion you arrive at about that pattern or set of examples that uses inductive reasoning. So conjecture again is a concluding statement that is reached using inductive reasoning. And so for our first example, we're going to look at a pattern and write a conjecture. Remember, conjecture means a concluding statement that is reached using inductive reasoning. So we're going to look at a pattern and come up with a statement describing that pattern. That will be our conjecture. Okay, so we're going to look at the pattern first. So we notice that we go from 2 to 4, then from 4 to 12, and from 12 to 48, and then from 48 all the way up to 240. I want you guys to pause the video to look at that pattern and see if you can identify what the pattern is. Either you're adding or multiplying. We are getting larger, so we're most likely not subtracting or dividing. But I want you to figure out what the pattern is for how to go from one term to the next. If you need more time to try and figure it out and you want to try and answer that puzzle, go ahead. Otherwise, we're going to go ahead and continue. The pattern here can be found by realizing that you are multiplying each time, but we're not multiplying by the same number. We're multiplying by a new number. From 2 to 4, we multiply by 2. But then from 4 to 12, you would multiply by 3. From 12 to 48, that's actually 12 times 4. And then 48 times 5 is 240. And so our conjecture could be this. The numbers are multiplied by 2, then 3, then 4, then 5. The next number will be the product of 240 times 6. We would multiply by 6. Or 1,440. So our answer, the next item in the sequence, is 1,440. Okay, but that is our conjecture. You're explaining what the pattern is and how you would achieve the next item in the pattern. That's our conjecture about this set of examples. Okay, for example 2, we're going to do some of the same things. I'm going to let you try and do this part a little bit more on your own. And then we're going to check by drawing our next figure to make sure it works. And so this is our first term. It's actually a figure. It's made up of 3 segments. Then this figure is made up of 9 separate segments. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this next one is made up of 18 of these smaller segments. And so you'll notice we go from 3 to 9 to 18. So as we are looking for a pattern, to go from 3 to 9, we are going to add 6. From 9 to 18, we add 9. And so we can use that to help figure out what are we going to add to get to the next figure. And so the pattern here, you might notice that 6 is 3 times 2, and the next number we add is 9. That is 3 times 3. And so you can see that we're just going to add the next multiple of 3. So we would do 3 times 4, which is 12. So we're actually going to add 12 to this next one. So our conjecture could be this. The figure will increase by the next multiple of 3. And that's kind of based on the fact that there are 3 sides to a triangle. So when we make our triangle bigger, we're increasing by the next multiple of 3. Okay, so in this case, if we add 12, the figure is made of 18 plus 12, 30 segments. So the answer is using 30 segments, and we can draw that. You can kind of see the pattern visually by having one triangle, then adding another row underneath it to make this pyramid shape. So the next row has 3 more, then the next row has 4 more, and so the next row should have 5 more of these triangles. So it should look something like this. And if you do count all of these segments, you would count 30 total segments. So that works. All right, now we can have conjectures made about more numeric patterns again. This is going to be another opportunity for you to write a conjecture about this pattern. So there's 2 steps here. Step 1 is to look for a pattern. Step 2 is to write your conjecture. Remember, that's your conclusive statement. Explain what the pattern is. And then step 3, predict the next item in the pattern. I want you guys to pause the video to look at this and try and do these 3 things. When you write your conjecture, you're going to write what you think the pattern is, explaining that pattern, and then you're going to predict the next item in the pattern. Alright, if you need more time, go ahead and pause the video. Otherwise, these are the answers here. Alright, the pattern you should notice is 1 even can be written as a fraction 1 over 1, and that denominator is the perfect square. You could even write it as 1 squared. It would still be 1. 1 divided by 1 is the whole number 1. And you don't necessarily see it with the first one, but the rest of these, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. And so the pattern is that the next term has a denominator that is the next perfect square, or next integer squared. So the next item in your pattern would be 1 over 6 squared, which is 1 over 36. Alright, let's move right along. And so once again, we've got another opportunity to write a conjecture about the patterns you notice. I'm going to let you guys pause the video and take a look at this and try and figure out what the pattern is based on the number of circles creating the triangle and the numbers given below, and write that conjecture, and then check your answers. So once again, pause the video so that you have enough time to do that. Alright, if you are ready to check your answer, this is what we should get. Alright, the pattern you should recognize is that we're adding the next number of circles, so we are adding 2, then 3, then 4, so we will add 5 circles next. So this is your conjecture. The next figure will have 5 more circles, or 10 plus 5 equals 15 circles, and the drawing should look like this. All right. Let's keep right on going through these examples. We've got some more to talk about. And now we can also have algebraic conjectures, which talk about the concept of numbers. And this is where it's going to require you to think a little bit more, because you aren't given the pattern necessarily. We're going to come up with our own examples to help justify this. So let's take a look here. This is your statement. We want to make a conjecture, a conclusive statement about the sum of an odd number and an even number. Sum means we are adding. So I'm going to list some examples. I'm just going to pick some odd and even numbers to add together. Let's add 1 plus 2. That's an odd and an even. We get an answer that is 3. Let's try another odd and even. Let's try the number 3 plus 4. Odd and even. 3 plus 4 is 7. You can come up with any number of other examples. I'll just give you a few. 5 plus 10, that's 15. If you look at these answers, the things they have in common is that they are always odd numbers. No matter how many examples I came up with, if I add an odd and an even number, the sum will be another odd number. So the pattern is that each answer is odd. So here's our conjecture. The sum of an odd and even number is odd. And because this is the way the numbers work, this is always going to be true. The sum of an odd and even number is always true. And that conjecture is actually your answer, because they're not asking you to predict anything else. Okay, so we can make a similar conjecture about the product of two odd numbers. So you want to start by making examples, look for a pattern, and then make your conjecture. Okay, I'm going to let you pause the video to be able to work these out and come up with some of these on your own. Alright, hopefully you've gotten some examples written down. Here's some examples I chose, and then we should have the same pattern and similar conjectures. If you need more time, pause the video. Otherwise, here we go. Alright, you should notice in whatever examples you chose that the answer is always an odd number. That's really the only pattern we have, and you can kind of be guided towards that by looking at the words they use. They point out that you're taking the product of two odd numbers. And so our pattern tells us what we can write as a conjecture. The product of two odd numbers is odd, and that is your conjecture. Okay? Alright, now here's one other thing we can do. We can use conjectures to help us make predictions. We're actually going to come back to this example and do this one in class. So make yourself a little note. We'll come back to this one because I want to share with you in class about how to make those predictions. But the other main idea we want to talk about in this lesson is the idea of a counterexample. And a counterexample has this definition. A counterexample is any single example that proves that a statement is false. Could be a number, could be a term, could be a drawing that shows that a statement is actually false. So we're going to look at how to come up with counterexamples in this next example. Example 8, we want to find a counterexample to show that each of these statements is false. First of all, here's our statement in part A. If n is a real number, then n squared is greater than n. We need a value of n that would make this actually false. At first glance, it seems that this is going to always be true unless you remember that values like 0 squared is just 0. In that case, your answer is not greater than 0. It is equal to 0. It's equal to itself. So our counterexample is n equals 0. All right. Why don't you try and come up with counterexamples for parts B and C? This is another situation in which you'll have to pause the video, and then you can continue playing the video here at the end to see what examples I've chosen. All right. If you need more time, pause. But otherwise, these are some counterexamples we get for these statements. All right. This statement is false if k, j, and l are not collinear. There's nothing that says they have to be collinear, so K could be out here. In this case, JK and KL are the same. And then our counterexample for part C would include a right angle. These are supplementary,